All right, it's Advent of Code day 21. Dice. Losing player number of dice. Okay. I see. We're just given the two starting positions. 3 times forward. Okay. Seven and 2. What do we want to know? 3 times forward by the value of the space. Uh-huh. Okay. 4 and 8. We're going faster than this, huh? Nope. Uh, hmm. Hmm. 2. Like that. Ooh, rank 1. Cool. That hasn't happened yet this year. Well, that was a great day. Okay, so let's talk about this problem. So what was going on here? Yeah, so we have this circular track, I guess, with 10 spaces. And the players are sort of circling around the track, according to some rule, which we'll talk about in a sec. And every turn, you move to a new space, and you get points equal to the number on that space, right, from 1 to 10. And if you get enough points, the game stops and you win. So part 1 and part 2 are like pretty different here. But anyway, in part 1, right, right, how do you move? You roll some die 3 times, and then you move forward like the sum of the spaces. So in part 1, the die is just counting up from 1. I suppose really what we ought to do is this. So that was part 1. Right, so in part 1, the die is just counting up from 1, and you stop when you get to 1,000 points. So here's my part 1. Everyone starts with a score of 0, right? They start with their initial positions. And, the first player rolls 3 dice, moves that far. Mod 10, right, because the board is circular, so you're rotating around. And then mod 10 gives you a number from 0 to 9, but these scores are supposed to be labeled from 1 to 10, so that's why the +1 here, right? So you score that many points. If you have 1,000 points, then you won. And it says to print out the score of the losing player times the number of times the die was rolled. Right, so that's also the value of the next die, which is what this thing is, or, well, that's not quite right. But anyway, this is the number of times the die was rolled. This is the score of the losing player. The player didn't win, then player 2 gets a turn. So, he rolls 3 times, advances that many squares, gets points. Okay, so that was part 1. And then in part 2, so part 2 is weird, I think. I don't know. Anyway, you get a die, which is basically a D3, right? It can land on 1, 2, or 3. And this is basically asking for like the probability that a player wins, but they don't want to say probability, I guess. So instead, we're talking about like the count of the number of possibilities where the player wins, right? So the problem describes it as like you get a different universe. You get 3 different universes when you roll a die. One in which the number came up 1, 2, 3. Anyway, it's very similar to counting the probability that the player wins. I guess it's easier just to think about the problem's formulation. Okay, so how did I do this? I did dynamic programming, DP. So the point is, so as we can see from the example that like we can't just brute force this, right? This number, I didn't even count how big it was, but it's a very big number, right? If we try to enumerate this many universes, it's going to take forever. It's never going to finish. But all that we really care about, if you think about it, is where the players are and how many points they have, right? It doesn't matter like exactly which sequence of die rolls got us to that position. Right, so you can imagine the DP idea is basically like do the brute force solution. But then if you see a state that you've already seen before, instead of recomputing it, just return the answer that you got last time. So let me try and unpack that a little bit. I guess first let me try and show why this is a brute force solution. First let me say what this function even does. Given that player A is at position P1 with score S1 and B is at position P2 with score S2, how many where player A wins right? So like given the current state of the game, how many universes does each player win in? Yeah. So that's what it's supposed to do. And this is, most of this is just a brute force implementation of that question. Right, so if player 1 has 21 points, then they win in one universe, and the game's over. Player 2 wins in 0 universes. Player 2 has 21 points, they win, player 1 wins in 0 universes, player 2 wins in 1 universe. Ignore this for now. And then initially, right, we haven't recorded any wins for either player. Enumerate the 3 possible die rolls, right? So you roll 3 dice, each of which has 3 possibilities. So there's, 27 ways for this for loop, which are all the die rolls. Move yourself, assuming like player 1 is the current player, move yourself forward that many squares, update your score, and then recursively count the universes in which for the new game state, right? So P1 is always the player whose turn it is. So for the recursive call, it's now player 2's turn. So we're going to swap their positions, right? So player 1, we have to give the new position for player 2. Player 2's position, which is now the position of the current player to move, since it's now player 2's turn. The new position of player 1, who's the other player. The score for player 2, and then the new score for player 1. And this is going to return how many universes player 2 wins and how many universes player 1 wins, right? Because we swapped the arguments here. So we need to update, our answer with the results of this recursive call. And we need to swap back, right? Because this is where player 1 won, and this is where player 2 wins. The swapping is just an optimization, somewhat confusing optimization that I did. That's not important for the DP. You could, just have a flag of whose turn it is. That might be clearer. And then you just return that answer. Right, so if you ignore like a couple key lines here, this is just a straightforward brute force solution. And it would take forever. It would never finish, right? Because there's just so many universes to chew through. But if you memorize it, it does finish. So what is memoization? So that's these lines that we didn't look at yet, which is basically if you've already seen this game state, then don't recompute it. Just return what you calculated before. Right, so this is like a dict of right. So all we care about, for the game is like where they are and what their scores are so far. So if we've already been in that position, just return what we computed last time. And then once we compute the answer for a given game state, write it down in this dictionary. So how helpful is this? Like, do we really encounter the same game state many times? Well, we do. Because there just aren't that many possible game states. Right, P1 can be up to 10 things. And we know the scores are at most 20, because you win if you get 21 points. So how many game states are there total? Well, there's only like 4,000. I guess this is 40,000. Right, this is like 10 to the 4 times 2 times 2, 40,000. Which is really small, right? A computer can handle 40,000. It can't handle like quadrillion or whatever this number is, but it can handle 40,000. So if we know like the brute force goes through like, a quadrillion things, but there's only 40,000 game states, well, we must actually hit the same game state over and over and over again, right? Which seems like slightly unintuitive, because it seems like, different die rolls get you to different places. But like, the state space, like there's just not that many ways, the positions the game could be. It must be that many, many different types of die rolls can get you to the same place. So like we can use this fact about how big this dictionary is going to be to figure out what the running time of this is going to be, because this whole section of code only runs 40,000 times, right? Because otherwise, like we only fill in a new entry in the DP table 40,000 times, right? There's only 40,000 keys in this dictionary. So every other time we must just get into this, quick loop, right? We just return right away. So the total amount of time that we're going to take here is 40,000 sort of real calls to this function times like 27, which is the number of, possible die rolls that we have to think about, or triples of die rolls that we have to think about. Total running time, state space times non-recursive time for one call. So that's what, like, roughly 1 million, right? Because the point is, like this recursive call is just another call to this function, which is going to hit the DP table, right? So you can think of this as basically being free. And so the rest of it is all that we need to pay for, which is, as I say, 40,000 times 27. So that is how to do part 2 quickly. Oh yeah, and I should actually print out the answer to part 2. Not that. Maybe we can just do this. Oh. 311, yeah. 78. Okay. So cool problem. And yeah, dynamic programming is super cool. And it's, really useful for, often, actually, you can use it to solve a lot of games that have, especially, if you have a small state space, right? Because, like, you just need to consider, anyway, like this example where you can forget a lot of stuff, right? This is another way of thinking about DP, is like forgetting as much as you can. Like all the things that happen in this game is all the different die rolls, and there's like many, many possibilities of that. But in fact, like most of that history doesn't matter. All that matters is sort of the present state, right, which are the positions and the scores of each player. You don't care how you got there. And so a lot of solving DP problems is figuring out exactly what you can forget about and what you have, making what you have to remember as small as possible. Okay. So that is about all I want to say about day 21. See you tomorrow.